Hello, this is the third video for Graphs and Networks Series 3 on Further Graph Theory for OCR Discrete Further Mathematics, and introduces Orr's theorem. Orr's theorem states that given a simple graph G, remembering that simple means a graph with no loops or multiple edges, with n greater than or equal to 3 vertices, if for every pair of distinct non-adjacent vertices, say v and w, the degree of v plus the degree of w is greater than or equal to n, remembering also that degree is sometimes known as the order of the nodes, then G has a Hamiltonian cycle. So essentially, this theorem states that a graph with sufficiently many edges must contain a Hamiltonian cycle. Consider the graph below with 5 vertices with degrees 3 and 2 and 3 and 3 and 3. For every pair of distinct non-adjacent vertices. So if we looked at that 3 and that 2, we would see that those add up to 5. And we know n is 5. But also simply because of the numbers, you're not going to have any degree pairs that are less than 5 or 6. Therefore, we can say that G has a Hamiltonian cycle using Orr's theorem. In this example here, we can see that each of the 5 nodes has degree 2. And so for every pair of distinct non-adjacent vertices, v and w, so for example this one and this one, the degree can only add to 4, and therefore, given that n is 5, we have a situation where those 2 degrees must be less than n, and so Orr's theorem does not apply. But we can see there is a Hamiltonian cycle. So you could do a cycle right round that graph, and therefore we have to conclude that Orr's theorem is a sufficient condition to show a graph is Hamiltonian, but if Orr's theorem does not apply, it does not mean that the graph is not Hamiltonian. Looking at the example, we're asked if the graph satisfies Orr's theorem. Well, let's have a look at some non-adjacent pairs. Well, A and B are not connected, nor are A and D, or A and F, or we could choose to look at BC, or CD, or DF, or EF. Let's just check the orders of those nodes. So we've got a 4, a 2, a 3, a 3, a 2, and a 2. So A and B would be 5. AD 4, AF, the degrees added would be 4. So I should say that these are not the arcs, the list I've got here, they are just the pairs of non-adjacent nodes. BC 6, CD 5, DF 4, and EF 6. Now I can see that n equals 6 because there are 6 nodes or vertices. So there's any number of examples there where the degree of v plus the degree of w is less than 6. And therefore it does not satisfy Orr's theorem. But there is at least one Hamiltonian cycle. For example, if I start at E and then go to D, down to B, across to F, to C, to A, and then back up to E again. So to summarise, Orr's theorem gives a sufficient but not necessary condition for a graph to be Hamiltonian. So if Orr's theorem is satisfied, that does imply a Hamiltonian graph. If it doesn't apply, then the graph might still be Hamiltonian, but we'll have to find a different way of showing it. In the next video, we will investigate planar graphs.